All right, so for the warm-up problem today, we're going to do more conversions of 2D bond line structures to chair structures. All right, so on the exam, what I might give you is a 2D structure and ask you to draw some chairs. And like I said in class yesterday, I want you to practice drawing chairs on your own. However, on the exam, and you'll see on the practice exam, I give you some chairs already. So I'll just draw 2 chairs already drawn. And our job is to change the 2D structure to the chair structure. All right, so first thing I really like to do is I like to number my 2D structure. All right, so if we were to number this using IUPAC naming, we've got some groups to consider. Over here, we've got a tert-butyl. Over here, we have an ethyl. Over here, we have a methyl. If we're IUPAC numbering, which one would be number 1? Tert-butyl, because it has a B. We ignore the tert and sec when we're alphabetizing these. All right, and then I'll number going to E, because that's next. And just for fun, let's name this entire molecule. What would it be named? It would be 1 tert-butyl, 3 ethyl, 5 methyl, cyclohexane. And there shouldn't be a space here. That was my mistake. So we'll slide that in and show that there's no space. All right, so now we've got our numbering system. You see how we went clockwise? We'll do the exact same thing in our chairs. So I'll go 1, 2, 3, 4, 5, 6. All right, off of carbon 1, we know we have an axial substituent sticking straight up because that carbon's puckered up. And then the equatorial will be pointed in this direction. All right, so on carbon 1, what should go in this highlighted spot? And remember, carbon 1 is right here. I just arbitrarily picked any portion of the chair, and you're welcome to do the same, right? All right, so off of carbon 1, what will be closer to our eye? The tert-butyl group, absolutely. So we can go ahead and we can say, all right, tert-butyl group will be here. What does that mean goes here? An assumed hydrogen. All right, and then off of carbon 3, right here and right here, we also have a carbon puckered up. All right, so what's going to be off of the axial position here? Oops. So what I mean is what's going to be sticking up? It'd be the ethyl group. All right, so I'll do that. What's going to be sticking off right here in the equatorial position? Hydrogen. All right, so I'll go ahead and plug that in. All right, and then we go all the way over to carbon 5, puckered up. So we'll have an axial pointed up, and then equatorial. What's going to be axial? The methyl group. Okay, so that means we would have a hydrogen right here. And this makes sense, right? So if we're looking down on this molecule as a little stick person, all 3 of these groups are closer to our eye. Does that make sense? Compared to the hydrogens that are also coming off of those carbons, those hydrogens are further away from our eye. All right, so now what we'll do is we'll do our chair flip. All right, we can do the same sort of thing, but this time with our chair flip, I'm going to imagine little hinges here. I'm going to say, all right, what was my footrest is going to be spun up. What was my headrest will be spun down. So we're going to do our chair flip like that. All right, according to our numbering system, what's going to be right there? 2. 2 was the carbon on our footrest previously. So I'll say, all right, this is 2. Then I'll say 3, 4, 5, 6, and then we'll loop back around to 1. All right, so we're still doing the same thing. We're doing 1, 3, and 5. So let's do carbon 1 first. Carbon 1 is a little harder to draw in this configuration. It's going to have a group kind of sticking down in the back and then equatorial out this way. All right, so off of carbon 1, over on the right-hand side, we said off of carbon 1, we have a terp-butyl group. All right, will that terp-butyl group in our new chair structure be axial or equatorial? Equatorial, because it was axial previously. So now we can go ahead and we can say, all right, it's going to be sticking out that way, which means our hydrogen, which was equatorial off of carbon 1, will now be axial sticking down. All right, now we go to carbon 3. Carbon 3 again has an axial and equatorial substituent. If we go back to our first chair structure, the ethyl group was kind of sticking up closer to our eye in an axial orientation. What about in our second structure? Where should it be? Equatorial. So I'll say that that ethyl group is now equatorial and the hydrogen must be axial. All right, and then carbon 5. Again, we have axial and equatorial. We can go back to our original structure and say, all right, in carbon 5, this methyl group was axial, which means off of carbon 5 in our second structure, it should be where? Equatorial, which means the hydrogen must be axial. All right, so let's imagine our little stick person again, looking down on this. Can you still see how all three of these groups, the terp-butyl group, the ethyl group, and the methyl group, are still closer to our eyes than the hydrogens? So even though we did this chair flip, there's still wedges in space when we're looking down on this. Does that make sense? So it takes a little time to get good with. Like I said, you might want to practice with your model kit if you're really having trouble with this. That's what did the trick for me. Once I played with my model kits for like 4 hours, I was like, wait, I get it. But it took me like 4 hours of ripping apart models and being frustrated before all of a sudden it clicked with me. Yep.
So in this case, the whole thing should be trans at the top, right?
Yeah, so we'll talk about, so the question was, is this all trans or cis? We only use cis or trans when comparing two identical things. So in this case, because they're all different, we can't really do that, but we'll learn how to name this next chapter in order to be more specific. All right, so now, $1 million question for everybody. We've got these two chair structures. Which one is more stable? Left or right? Right, why? Everything is spread out and away from the ring system. In fact, there's a fancy science term that we use to describe the one on the left. These groups are all going to kind of bump into each other on the same face up there. Kind of see that? This interaction right here is referred to as a 1,3 diaxial interaction. 1,3 diaxial interactions are really destabilizing because when they're all pointed up in the same axial direction, they'll actually bump into each other in space. It really doesn't want that to happen, so instead it'll flip out. So if we were to draw this equilibrium arrow to represent the true equilibrium, we'd say this is almost all going to go to the left. Tiny, tiny, tiny bit will favor, or sorry, all go to the right. Tiny, tiny little bit will be on the left-hand side. Make sense? All right. So let's grab that in-class activity and we'll walk through the first one together and then I'll let you practice the rest. All right, so in-class activity, we're going to look at trans 1,2-dimethyl cyclohexane. All right? Or actually, shoot, we already did this one in class yesterday, didn't we? All right, let's change it. Cis 1,2-dimethyl cyclohexane. I didn't realize we did our example on accident. All right, so we'll do our 2D first. And I'm just going to number any which way I want because it's my molecule. All right, we've got methyl groups coming off of carbon 1 and carbon 2. Should they both be dashes, both be wedges, one a dash, one a wedge? How would we orient this so that it's cis? both the same, right? Because cis means same side. All right? Does it matter if they're both dashes or both wedges? No. So I'll just go ahead and fill this in with a wedge here and a wedge here. And that would be our 2D bond line structure. So cis means that they're the same, trans would be opposite. All right, so we're good to go. That's our 2D. Now we'll go ahead and draw our chairs. Okay, so we've got two chair structures. In our original structure, we drew it going clockwise, so I'll stick and do the same. 4, 5, 6. All right, off of carbon 1 in our first structure, we would have an axial substituent sticking up, equatorial out. All right, the methyl group for carbon 1, and let's imagine we're kind of looking down on this. The methyl group on carbon 1, meaning this methyl group right here, would it be axial or equatorial? Yep.
Okay, so like, I have a quick question.
Yep.
I just want to like go back like 3 seconds. So you said it doesn't matter if like they're both like wedges or if they're both like dashes. Is that right?
Yeah, so the question was, does it matter whether I draw it like this or like this? Is that what you mean?
Yeah.
Okay, yeah, that's a great question. Do you think these are the same or different compounds? Imagine I have a pancake flipper and I pick this up and I flip it over. It's the exact same compound. So we could draw it either way. It would still be the same compound, just one's flipped over. Good question. All right, so going back to the highlighted methyl group. We said off of carbon 1, it's a wedge, which means in the chair structure shown right here, would it be axial or equatorial? Axial, okay, so I'll go ahead and even just write in Me for methyl, which means that we would have a hydrogen there. I didn't show it, but we know that in reality there's an assumed hydrogen that must be a dash, right? Okay, now we go to carbon 2. Over here we'd say, all right, carbon 2 has this methyl group. Would that methyl group in green be equatorial or axial? Equatorial. Which means the hydrogen must be axial. Make sense? All right, I'm going to slide this chair over just to make more room. Same idea as before. I'm going to take my footrest here. I'm going to swing my footrest up, take my headrest, and pull it down. So I'm flipping my chair. All right, what's this carbon going to be? Be 2, as I haven't shown here. So I'll say 2, 3, 4, 5, 6, which means 1 must be right there. Make sense? All right, so off of carbon 1, we would have an axial substituent sticking straight down and an equatorial going that way. So again, we're looking at the yellow highlighted methyl group this time. And again, we can imagine our little person kind of looking down on this. Will the methyl group go where the orange, oh, that's not orange, that's blue. The pen is blue. All right. Which spot will the methyl group be in? Let's think about it. Off of carbon 1 originally, not only did we say the methyl group should be closer to our I, but in the first structure, it was axial. So let's address both of those questions. So if it was axial in the first structure, in the second structure, it should be equatorial. So is orange or blue equatorial? Orange. But you notice how the methyl group here is closer to our I than that blue circle? It still works. So I'll go ahead and kind of empty this out with a hydrogen. Let me fix this a little bit and you'll see why. Okay, and then off of carbon 2, we would have an axial and equatorial substituent. Off of carbon 2, same question. Where would the methyl group be? Would it be in the orange spot or the blue spot? Orange, because it was over here, equatorial. It must be axial now, which means the orange spot would be the better fit. All right, so I'll go ahead and plug methyl group in here, and I'll put my hydrogen in there. All right, so these are two possible chair structures. Which one's more stable? Let's ask ourselves. There can be ties too. So we said that large groups prefer to be equatorial, kind of pointed out in a way. See how in the first structure, we have this methyl group pointed out in a way, the other group's axial. In the second structure, we have this group equatorial pointed out in a way, but the other one axial. So what do we think?
The first one, because the second one has kind of a Gauss interaction going on.
So the question was about Gauss interactions. A Gauss interaction is kind of the same idea as a diaxial interaction. So what we typically look for is we want to minimize the number of large groups and the axial orientation. Which one's better? I'd say they're the same, right? Both of them have a methyl group in the axial position. So I would say these would be equal stability. All right, so what I want you to do is try to work on the remaining problems with groups, ideally. And if you can, pull out your model kits, try to learn how to build models, and then I'll float around the room and try to help you with this one. Sound good? Yeah.
For example, there's cis and trans, but there's not identical substituents in there. Are we flipping substituents?
Yeah, so with cis and trans, the identical substituents that we're comparing would be the assumed hydrogens coming off of those carbons. Okay. Yeah, so cis and trans can also be used to compare identical hydrogens, both being wedges, both being dashes. Does that make sense? In fact, let's draw this one out just so we avoid any confusion. All right, so on this one, got a cyclohexane. I can number any which way I want because it's my molecule, and I'm building it. All right, so off of 1, we have a 1,1 dimethyl ethyl. It's a little bit confusing to think about, but the root of this word is ethyl. So I'm going to go ahead and say off of 1, I've got an ethyl root. And then if I think about numbering this, I'd say, all right, the ethyl group, if I number out, has 1 and 2. So what does the 1,1 dimethyl mean? Yeah, the dimethyl means off of carbon 1 of our ethyl root, we must have 2 methyl groups. What is this group often referred to as? Tert-butyl. You can see why we like saying tert-butyl over 1,1 dimethyl ethyl. It gets super overwhelming having so many methyls and ethyls thrown at you all at once. All right, so that's off of carbon 1. Carbon 4, down here we have a methyl group. All right, so now the question is saying cis. So what does that mean? Same side. So let's go ahead, and what I'll do is make these both wedges. Like that. And what this means in terms of cis is both of these hydrogens right here that are assumed, these are the identical things that we're comparing. Both those hydrogens are dashes, therefore it's allowed to be called cis. Yeah, great question. All right, so I'll let you guys get working on this, and then I'll float around the room to help out.